Hi everyone. Oh my God, so many people. Yeah, so I'm David and I'm going to talk a little bit about Albion Online. This is mostly a technical talk, but I will try to offer something to everyone here. This is Albion. We have a booth directly to the main hall, so you've probably seen the game. Maybe you've talked to us already. So just a very, very quick overview. The basic idea behind Albion Online is we want to be a mixture between EVE Online and League of Legends, basically. So we're EVE Online as far as like crafting goes, guild warfare. We have like one world for everyone. But at the same time, we're combining that with really fast-paced League of Legends style combat with skill shots and everything. So that is the basic proposition of Albion. The whole thing started like 4 years ago. We started as a very, very small team with only 4 guys. We have a private investor who came up with the idea, who was like, hey, let's do an MMO. I have this vision. And we kind of started building that. And this part is important to understand because I and a couple of other team members, we have a lot of experience in the games industry. I had been making games for more than 10 years when we started Albion, but none of us had ever done an MMO before. And now suddenly we were doing one, and we were doing a cross-platform MMO. So right now we're supporting Windows, Mac, Linux, Android, iOS, and like I said, we're doing one server. So all the players on all the different devices are playing on the same server. So that was a tremendous challenge. But I think we've done a pretty good job so far, and right now we're in closed beta. We have more than 100,000 founders, so people who bought founder packs who are playing the game right now, and if you want to play the game, you can just go to albiononline.com and start playing yourself. So yeah, let's get to the interesting part. What technology are we using? Well, obviously, we're at Unite, so we're using Unity. It was an obvious choice. Basically, it's a powerful engine. It was inexpensive. It was accessible. So we quickly went with that. The cross-platform aspect, to be honest, was a target of opportunity for us. So originally, we thought, okay, if this was a PC-only game, we'd be totally okay with that. But since Unity offers to easily port to different platforms, we went with that, and we actually managed to put the game on mobile devices as well, which is totally awesome. Apart from that, obviously, when you do an MMO, you need to have databases, and we're using 2 different types of databases. We're using Postgres, which is a very powerful, very fast SQL database. We're using that basically whenever we need to do real complicated queries on data, like the marketplaces in the game are such an example, right? You need a strong query language for that. But for the heavy lifting, as far as the game goes, we went with Cassandra, which is a NoSQL database. I'll say a few things about that in a moment. And on the networking side, we decided to go with Photon. Photon is a networking middleware which supports UDP and TCP. UDP both reliable and unreliable as you need it. And it was basically a good choice for us because Photon comes with a server framework which is you can program in C#. So we can actually program the server and the client in the same language. We can share code between the two, which is actually a very, very good thing, and it seamlessly integrates with Unity, which is also cool. I want to say a few words about Cassandra because that is probably the most unusual technology I have on my slides. Cassandra is a NoSQL database, originally developed by Facebook, but it quickly became an Apache project. It's written in Java. And the interesting concept behind it is essentially a distributed hash table. So the advantage of that is it is optimized for very, very high throughput. You can like push insane amounts of data into that, and it won't break a sweat. And it can scale horizontally, which was the important thing for us, right? Because we have that one world. We potentially need to support like hundreds of thousands of players in one world on one database. So we wanted to pick a database that can actually scale by just adding more database servers. and Cassandra can do exactly that. It is also redundant, so if some of the database servers fail, the database is still up and running, which is also awesome. The restriction you have, on the other hand, is that the queries you can do on that are kind of limited. Cassandra has an SQL-like query language called CQL, but it is nowhere as near as powerful as SQL. So there's no joins, there's no complicated where clauses, stuff like that. But it can do a couple of other interesting tricks. So it is kind of an interesting trade-off. Okay, so after we had picked our basic technology, we thought, okay, basically we want to have a server that works without Unity, which is a strange thing to say at a Unity conference, but the truth be told is we didn't trust Unity. Well, Unity is a great tool, it's totally awesome, but it's made for like clients, right? It's not something I personally want to have on the server. I know people are doing that and apparently doing it successfully. We explicitly didn't want to do that. And while we're at it, we thought, wouldn't it be cool if the client worked without Unity as well? Because that does have advantages, right? Just think about the tools you can build, like especially like you can have headless stress test bots, and we do have that. We literally have a Albion command line client which is fully featured and which does not depend on Unity, which can actually log into the server, and we can spawn hundreds of instances of that and do stress testing on the server, and it just works. So we wanted to use Unity only as a rendering front end, which still is a tremendous task. But basically what we came down to is we wanted to implement all the basic game features independently from Unity. So we needed to have our own system for levels, for game objects, for collision, for pathfinding, and stuff like that. So what we came up with is basically an architecture like that. And this is, in a nutshell, you could say, this is kind of a model view control thing, right? We have the server, and every game object is on the server. Obviously, it's an authoritative server, so it has full control over absolutely everything we do. And the server will send the game object over to the client as soon as the client sees that. And our client is just a DLL. It's just a library, right? It's just C# code, nothing else, no Unity in here. And the client will first of all create a replica of that object that has the same properties that the server told it about. And the client can also like request an action from the server if necessary and say, hey, I want to do this, and the server will respond. And then on top of that, we're adding Unity. Basically, Unity is loading our client as a DLL, and then Unity acts as a view on top of that data model. So for every game object, Unity will create an object view, and this object view is now responsible for graphics, for animation, for input, for sound, so for everything that is super important for the game, but essentially not gameplay. But whenever a gameplay decision is to be made, Unity will take the input from the user, but actually go to the client library and say, hey, the user appears to be doing this or that, and then the client library is actually responsible for talking to the server about that. So this is our architecture, and I must say it is super powerful. We're super happy with that. Because basically having these separations in the code actually simplifies development in a lot of ways, right? You have less dependencies between things, simple as that, right? If you have a couple of walls in your code, then the number of dependencies between different modules are just lower. And like I said, it is totally awesome to be able to tools like a standalone command line client. That, in our opinion, was totally worth it. Okay, looking at the server farm very quickly, we have a whole bunch of different server types. Actually, the most important ones are the ones over here. Those are the front-facing servers. There's obviously a chat server that's for chatting. We have a login server that does account management, logs in users, stuff like that. And then we have a bunch of game servers that host the actual game world. And as the player moves through the game world, the player may have to change from one game server to another. So the user is actually always connected to a particular game server depending on the area in the world he or she is in. And that connection will then change as necessary. In the background, there's a whole bunch of other servers. There's like a world server that is responsible for everything that happens globally in the game world. For instance, like guilds or parties are such a thing, right? The members of a guild can be in totally different corners of the world. So not a single game server is responsible for the guild, but the guild still has like a shared bank account and stuff like that. So you need a single point of access for global stuff like that. That's our world server. Marketplace server obviously deals with the marketplaces. The gold market server is like, we have like a stock exchange in the game where players can trade in-game currency against real money currency. Well, that is handled by the gold market server. We have a server that does only statistics. We have one that calculates all the rankings that the players are so fond of. And the back office server is kind of the spider in the net here. It controls the whole farm, controls farm startup, farm shutdown, and it's the single point of access if you basically want to talk to the server farm as a whole. And then we have a lot of like databases in the background for separate things. You can see that we use actually separate database instances for separate tasks, which enables us to move them to separate servers should they ever be so busy that a single server cannot handle them all at the same time. Okay, our game world is relatively conservative. Basically, we're splitting the game world into what we call clusters. A cluster is an area of roughly 1 square kilometer size. That is also a size that like a tablet can easily load and handle. We currently have like 600 of these, so the world is quite massive. The next world, which we're currently working on, will be about twice that. So big stuff coming up. So this is a screenshot of our world map. Basically, all of these little areas you can see here are individual 1 square kilometer areas. And if you look at the mini map down here, you get an idea just how big that game world is right now. You can see the little rectangle there that shows the current section you can see. So what we're doing with that is we're basically distributing these clusters among the game servers. We currently have 6 machines running the world. So every server, they're quite ordinary machines. They're like Xeon Deca core machines, so nothing fancy there. So each is running roughly 600 of these areas, plus of course instanced areas, like, you know, there's instance dungeons, there's like player islands and stuff that is created dynamically as players enter that. And yeah, but most of that is like statically assigned to a particular game server. And as the player moves around the game world, we basically do the handoff through the database. So like you're leaving one game server, you put in the database, you go to the next game server, you're fetched from the database again, and there you go. So players don't really realize they're moving from server to server, but it's actually what happens. Originally, we had the plan to like distribute the server farm across the Atlantic. So in an early setup, we actually had game servers in America and other game servers in Europe, and players were able to seamlessly move between them, right? The idea being that like American players get a better ping with the American servers and European players get a better ping with the European servers, but you can still move over seamlessly. We did that for a while, it did work, but it was a lot of trouble, obviously, because like the Atlantic is a terribly huge place, and you do get connection losses inside your server farm, which are trouble to deal with. We dealt with it, but in the end we decided it's like not worth the trouble, so we just moved everything to one location now, and it's much more stable now. Okay, talking a little bit about what the game server does internally. one very important decision we made early on was that we made the gameplay decisions inside a single area of the game single-threaded. First of all, that sounds like a terrible idea because that obviously limits how you can scale. But like early experiments showed that, if you try multi-threading, you have two options. Option one is you do a lot of locking, because like even in simple gameplay situations, you have a lot of interactions between game objects, right? It is very rare that a player does something that affects only him. Usually it affects a whole bunch of people around you. So either you're doing locking all over the place, which is also error prone, and will kill your multi-threading in the end, or you try to be extremely clever and use lockless structures and avoid locking all the way, and you end up with a lot of crazy race condition problems that are super hard to track. So after trying that for a couple of weeks, we thought, okay, no, this is totally crazy. We're gonna do the game logic for a single area in a single thread. So we basically have an event queue here, and everything that can be moved out to thread pools is obviously moved out. So there's a network I/O thread pool, player commands arrive, they're put in the event queue, and the cluster will deal with the events one after another. It can easily do tens of thousands per second, so that's not a big issue. The handling of a single event is very, very cheap. And then if you need to do database I/O, you put something in the database I/O thread pool, and if a result comes back, it's put back into your event queue. Same for pathfinding, same for logging, and so on. The other thing that we have is like an event scheduler, which is basically a glorified timer system. So whenever an object in the game needs to do something repetitively, it will just create a timer for itself. So a bottom line is there is no game loop in Albion Online. There just isn't, right? It is completely timer-based. Whenever a command arrives, it is dealt with as quickly as possible. And if you need to run an AI for a monster or something like that, you just create a recurring timer that like ticks as often as you want it to tick, updates the monster, and obviously as soon as the players move away from the monster will go to sleep, kill its timer, and not use any processing time anymore. So a bottom line is, if there's no player in the woods, then not only does the tree not make a sound, the tree will literally not do any work and not use any CPU time in that respect, which is obviously a good thing. Okay, and another big thing that that may be interesting for you is interest management. This is one of the most important things that a game server in any MMO does. Interest management basically comes down to the question, which player can see what? And that is important for two reasons. Reason number one is network traffic. The game areas are quite huge, right? I said 1 square kilometer. In that 1 square kilometer, you have around about 500 monsters which are roaming around. You have more than 10,000 interactive game objects. Most of them are trees in our game, but you can cut down every single tree in Albion, and every single tree will grow back, so they're all interactive objects that need to be synchronized over the network. And you can have realistically up to 300 players running around, right? The server can actually do much more, but 300 is something that you encounter very often. Most cities have 300 players running around at any given time. So you need to be very, very efficient here. You need to make sure that you're sending each player only the stuff he's currently interested in for traffic, for bandwidth reasons. And the other thing is cheating. Because you wouldn't believe it, like people used memory debuggers on our game pretty much on day one. Right? That's the MMO crowd. That's people who have already cheated in 5 other MMOs, who know exactly what to do, who know their tools, who know their workflows, and they're just applying it to your game immediately. And so the lesson learned is like everything you have in memory and everything that is in a network package somewhere is immediately known to some players. So you need to make sure you're only sending the information the players can actually see. Example, player becomes invisible. It's not enough to hide the model on the client. Oh no, you actually have to remove that invisible player from the network stream completely. Otherwise, he is not invisible, actually. So that's what interest management does. And so the way we're tackling this is we're using a grid-based hash here. So the whole area is split into cells of roughly 10 by 10 meters. As an object moves around, it registers with its current hash with its current grid cell. And both the objects and the grid cells can fire events. So a grid cell can tell you whenever an object has entered or left the cell, and you can also like subscribe to events on the object. The object can tell you when it's moved, when it has been destroyed. It can also tell you whenever it does something interesting. So it all comes down to subscribing to the right elements here. And then what we do is we create a so-called interest area around the player. Essentially, the interest area is an inner and an outer area. So whenever so I'm the player here, the red area is my inner interest area. Whenever something enters that interest area, I want to know about it. So I need to get all the network updates from that new object. And whenever something leaves the blue area, I'm not interested anymore. Right? The blue area is slightly larger so that objects don't cross the border too often. Whenever an object becomes visible for the first time, you need to send a bunch of information about, okay, there's this object and this is what it does, and after that it's only updates. So you don't want an object to continuously enter and leave the area. That's why the leave area is slightly larger. And yeah, basically it now just comes down to subscribing to the right events. So basically the player subscribes to enter events in all these cells, and it starts subscribing to the move events of the objects it's currently seeing. And that way you have a very, very efficient system that will immediately tell you what you're interested about. And it is really low overhead. It does use a lot of memory though. Surprisingly, like half the server memory goes into this interest management systems. It's gigabytes of memory just for these hashes and all the events that are registered all over the place. So that is a lot of memory that goes into that. We had a memory leak in that once. That was not fun. But yeah, it is super fast and super efficient. Okay. Now switching to the client side, this is probably something you're very interested in because this is now Unity. So the way we build Albion is out of tiles. Albion is essentially a tile system. So a tile is a prefab, essentially. It has a model, it has a 3D collider. If it's a ground tile, so we know where the ground is, we can basically raycast the exact ground height at any point. And in addition to that, we're painting a 2D collision per tile. This is the red stuff you see down here. So we basically put our own collision editor into Unity so the artists can like paint that collision for every single tile. And then when you assemble a level, the collision is essentially baked together, and you see the resulting combined collision here in the screenshot. This is like projected onto an actual level. So the reason we're doing it that way is twofold. First of all, this 2D collision stuff is super fast and super efficient. It is certainly much more efficient than an actual 3D collision detection. And the other advantage is, remember, we wanted to be able to do all of that without Unity, right? So this is something that actually gets exported to the server. So we have an export process that basically takes your Unity level and writes out a list of basically tiles that are used in that level along with the collision that these tiles have. They are put basically into an XML file, and that XML file can be loaded by the server, and so the server knows where everything is and where the collision is. And now here's the shocking part. We ended up using these XML files in the client instead of Unity scenes. So we're not loading our levels as Unity scenes. We're actually loading our custom XML format and then simply instantiating the prefabs to build the level out of that. And the shocking thing is that it's actually faster than Unity scene loading. which also speaks to the quality of Unity, right? So Unity is totally happy with like 30, 40,000 objects in a level, even on a tablet. It is perfectly happy with like instantiating 40,000 objects. It's really, really quick. Just like a Unity scene is a huge cumbersome block, and if you can avoid it, there's actually alternatives. Something like that does work. Okay. Another interesting aspect is like we have a lot of characters on screen, sometimes 100 and more. So how do we do that? How do we handle draw calls? The thing is, we're actually baking every single character and its equipment into a single mesh. So we can render a character with a single draw call, and like with a new Unity instancing feature, we can hopefully like even combine all of them into a single instanced draw call. The caveat, if you want to do that, is obviously that you have to use the same material on both the characters and all equipment items, which is a huge restriction. But you can see that our art style kind of supports that. There's very little texture in here. Most stuff is done with geometry. Most is relatively low poly anyway. Apart from that, we're using every trick in the book, right? There's several layers of vertex colors in there. We're using vertex colors to select specular areas on the character. In the baking process, we're actually modifying the UVs. We can even use that to like put guild logos on people's backs. You can design your own guild logo in the game with colors and symbols and everything, and we put that on your cape. This is all done in the mesh baking process, just by modifying the mesh sufficiently to represent your exact character. And we're doing all of that in real time, right? Every time you like put on a different hat, we're recreating the mesh for your character. And yeah, that really works. And you see that with that system, we can create a huge variety of different characters. So that is actually a very, very powerful system. Okay, almost done. One more thing that is quite interesting and funny: when you do an MMO, you have to deal with botters and cheaters pretty much on day one. Like I said, they used like memory debuggers and packet sniffers on our game pretty much from the start. And it turns out that .NET code is in fact very, very accessible to analysis. I was actually shocked when I tried out these tools for the first time. You can like literally take the DLLs out of the client, drop them into a tool, and it will more or less recreate your Visual Studio solution exactly the way it is. The only thing that's missing is the names of local variables, but everything above that level is exactly your code. And that's what people do, obviously. And they do that to extract all kind of information from our client. That's why like the interest management is important, so that camera hacking will not give people an actual advantage, right? You can easily move the camera out or something like that, but you will not see something you're not supposed to see. The most interesting thing is that people actually build bots directly into our client, and I have a screenshot. This is actually one of the bots that people have been building. You can see that they use the Unity UI to build the bot UI directly into it. You can like select what you want to harvest, and they're even using our pathfinding code against us. So I guess that kind of is I don't know. I take it as a compliment. Obviously, our client library is very, very easy to work with, even for even for people without who have not received instructions. But yeah. So while cheating is easy to prevent, right? We have an authoritative server. We're checking everything. We're only giving the client the information it's supposed to have. So cheating is not much of an issue. Botting is, and it is. Yeah, it is very, very difficult to prevent. We're doing code obfuscation. Obviously, it helps. It does not help much. It slows people down by a day or two. I hope that IL2CPP will work in our favor when it's available for desktop in the future, because that will make disassembling far more difficult. But yeah, apart from that, this is probably an ongoing battle for years to come. Okay. That's it. Thank you very much.